Hello, and I'll talk a bit about SEE-2-SOUND, which is something I was most recently working on. Uh, and Yeah, this will pretty much be like a short story, a short story of what I tried, what worked, what didn't work, and then I'll, of course, talk about the paper and share links about where you could find the paper and also how you could try out our code and that kind of stuff at the end. Um, yeah, that's about this, and I'll try to keep most of these. So I'll try to like talk about most of the stuff which isn't there in the paper. Uh, I think like that would uh, probably be a bit useful. I'll of course like talk about the method and how we do stuff, how we came across this problem and how we solve that. But try to talk about a few things which aren't there in the paper just because how it's written and that kind of stuff. Yeah, I'll try to talk about all of these things today. Uh, so let's start with a few things before I start the yapping. Um, this is slightly different from standard papers, more of a pipeline. Uh, so we find a problem and propose a pipeline for that, which is kind of different from a lot of papers out there. You might have seen a lot of these kind of papers very popular recently that describe a pipeline to do stuff, but it's it's a bit different than how usually papers are written, I guess. Uh, so yeah, that's I guess like all the background, and let's start by talking about what works and what doesn't. So I was particularly very interested in text to image and text to video models. These work really fantastically these days, and you have a lot of ways to solve these problems and a lot of ways to do like all kinds of stuff within these problems. So let's just take the problem a bit forward and say that you don't just want to generate image or video, but you also want to generate audio in a hopes towards doing like some sort of complete generation. Uh, so, so there are very different ways of modeling multiple kinds of audio. So you have modeling music, which is super popular, modeling speech, which is very popular as well, and you'll see a lot of things. And then there's background noise, which is what I was particularly interested in when I thought about like modeling or generating audio for images and videos. So I'll particularly talk about this one part when I say generating audio. Rest of the time in this reading group, I'll talk only about background noise, not about music and not about speech. Uh, so that is the only thing I'll talk about. So, so one, so while I was thinking about this, another thing we thought about is, so let's say you even manage to do this, you manage to generate lovely audio with images and videos. Some people have tried to do that problem earlier. Uh, there is also an evident qualitative gap in generating natural like audio, and this particularly comes from this really interesting capability that humans have. Uh, so humans have this really interesting capability that, let's say, if you're on a crossroad and you hear noise from all around you, it's very easy for humans to say how far away a car is and how far a car isn't, and what way it's coming from or what way it's going away, and that kind of stuff. In this example, just as just saying, so even if you manage to like generate audio for all of these videos and images, there's an evident qualitative gap in like especially this background noise. And this happens because if you notice, there's this really interesting
हमने किधर
quality that
रखना है लेके जाऊं मुझे बैठे रह
sorry, did someone say something?
I think they just forgot to mute. Sorry, muted them. Yeah.
Okay. Yeah, so humans have this really interesting qualitative aspect, which is, yeah, let's say, as I was saying in the example like a few minutes ago, let's say if you're on a crossroad, you just hear noises. It's very easy for humans to say, where noises are coming from, or where probably a car is coming from, how far away objects exactly are. You can almost like get the exact distance of objects just through hearing them. So this is a very interesting quality that humans have, and we potentially want to replicate this somehow in all kinds of audios that we generate. Uh, this turns out to be a big problem later on in how the method is formed. So, but yeah, this is a very interesting qualitative aspect that we particularly want to do for background noise. Um, Now, so the first thing I started doing was I tried to do some kind of end-to-end learning for this problem. Uh, just try to train clap plus clip style uh, models to do this. And it's surprisingly hard to do this just with like clap style models and nothing else. It's very easy if you were to do it for uh, very easy, as in you can just use the framework that these models, these clap clip style models have for uh, for doing stuff and say single channel audio, uh, which is quite common, or the mono audio. And you can also reasonably do it for two channel audio. So that's also very reasonably doable with this with these kind of approaches. But what I found out it's that it's very hard to learn a giant embedding space if you're trying to do this for uh, higher channel audios. Like spatial audio, for instance, often has 5 to 6 channels, where it becomes really hard to solve this problem in this way. So that is a bit about that is a bit about the background and the kind of problem that we're interested in solving. So uh, yeah, is there any question on like the kind of problem that we're interested in solving? Okay, yeah, I'll move ahead. So yeah, let's now talk a bit about the pipeline. Uh, so uh, so the first thing is it's very hard to collect spatial audio. Uh, the way I tried to train all of these clap style models earlier was that I stitched together spatial audio from mono audios, which isn't quite perfect. But I still tried to do that and tried training these models as a first step, which didn't seem to quite work well. But in general, if you want to collect a data set, it's super hard because you not only need a mic, but then you also need mics in particular positions, and you need multiple mics to collect this kind of data. As I guess I probably like to think, when problems become too hard, just make them compositional in nature. When we had all of these, when we had some of these LLM problems become really hard, people came up with chain of thought and thought maybe it's useful to think step by step. Uh, and then the same is very visible in vision as well. A lot of hard problems. Just people thought it would be good to solve one task at a time. So I thought about trying to do the same thing. Uh, yeah, you want to make this into a compositional problem instead. Uh, another thing you want to do is you want to use priors mono audio or just audio, so to say. All of these models that are trained on audio, background noise, or uh, any of these kinds of models, you also want to use priors from that somehow. Uh, so yeah, so that is also what we want to ensure while we are thinking about a pipeline to do this. And eh, particularly in this, we do this zero shot. Uh, so you can pretty much use any of these audio generation models to modify them into spatial audio generation models for videos and images. So let's start by talking about the pipeline and how you do the method. So uh, yeah, I guess like a bit earlier today when I was just thinking about like what to put on a few slides. Like the way I go through papers is just read figures. So I thought to do the same. Just put in figures and talk about figures. So let's do that. Uh, So we start with like some input media. Um, let's say for this pipeline, it's just like some image, some video, whatever you want. Uh, in this figure, it's an image. It's a Sora image, by the way. If you didn't catch that, this is a frame in the Sora video. So what you first do is first you do some kind of segmentation, and you get contours on each of the objects. Now, from the contours, you find these regions of interest. So, how do you exactly find these regions of interest from these contours? Let's talk a bit about that a bit later. For now, let's just say that I have these contours from plane segmentation, and I find out regions of interest somehow. How do I do that? Next slide. Wait, right now, let's say I do that somehow. So now what I do is try to generate single channeled audio for all of these individual regions of interest. And then I try to do, and then I say I do some viewing sphere tricks over here. So let's also talk about that later. But on a high level, this is what the pipeline consists of. And we have left a few very major parts of the pipeline. We haven't talked about how segmentation gets converted to ROIs. We haven't talked about how ROIs get converted to audios, and we haven't talked about how audios get converted into spatial audios that we want. So, uh, so we have left out a lot of things. But that is overall what happens during inference. So, so this is where the trick of converting segmentation masks or segmentation contours to ROI comes in. I'll not go through all of this, but essentially what you want to do is you want to solve an optimization problem on all of these individual contours and essentially get minimum bounding AABBs uh, 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 or I should probably just spell it out, access aligned bounding boxes for all of these regions of interest. So what you end up doing is that you solve this optimization problem for this polygon PK, and this is for each of the contour that you have. So now that you solve this, you get all of these AABBs for each of the contours, right? Uh, and so now that we got all of these AABBs, we can just formally define. So now we can use these AABBs as our regions of interest that we'll use later to generate audios. And
Hi. Sorry, one question here, because I was a bit interested when reading a paper. So like when you segment everything. Sorry, can you go back to the previous slide? So for segment everything, when you do like segmentation on that input media, I'm assuming like for the liver it'll be like one segmentation mask, right? So like will that be like converted into like two rectangle bounding boxes through that optimization kind of thing?
so over here, what would happen is it would get converted into a lot of different bounding boxes. So you'd have like one for every single mask. You'd have like one bounding box for every single mask that the segmentation finds out.
Oh, so like will like each bounding box like completely cover like the entire mask?
Yeah, it would at least cover the entire mask. Uh,
I
yeah.
see. Okay. Interest interesting. Kind of in the segment everything kind of like doesn't kind of like have very large regions, which kind of like make the bounding boxes too large and stuff.
But- Yeah. Yeah, makes sense. So so you're not finding the bounding box directly on the mask, which is like another thing. So let's say you have like let's say you have like this mountain in this image. So uh, you have you have this mountain in the left on the image. So you just find the polygon that bounds the mountain, and then you just get the bounding box for that polygon.
I see.
So
Okay.
uh, you so in general for all non-background masks, so over here I guess like a background mask would be the border, which is super large and probably like spreads across most of the image, if
Hmm.
and covers most of the area of the image, right? So for all the non-background bounding boxes, you would essentially end up with a very concise bounding box on the mask.
Interesting.
So
And you are mainly like getting rectangular regions, if I get it.
yeah, so we can do two things. The method uses these AABBs are rectangular regions, but if you see like, and these are received from equation, so you get these from equation two, but you can also use the polygons directly from equation two on this slide. So those would be tightly bounded polygons, and you can also use them directly. Uh, so we also show some experiments on that, but that doesn't seem to work so well. And uh, I, and we could probably show that this is usually because the diffusion models that will take in all of these images next, they have a hard time working with they have a hard time working whenever you have any of these inputs which have blank space of some sort. So if you use these polygons, they'll always uh, uh, they'll always have like some uh, they'll always have some like probably some discontinuity or not just be like uh, or really proper polygons, and that becomes a big problem for like inputs of these traditional diffusion models. So that's why we find that AABBs just work better experimentally.
Got it. Thanks a bunch. Yeah.
Okay, one more question. Sorry to interrupt. So, I saw that there was a depth estimation model which was being implemented on the previous slide. So, does it only contribute to separate the background and the foreground, or is the logic from it being used for or contribute for something else along the network?
Oh, yeah, I'll also talk about that. But yeah, that's I guess like a good question. I'll also talk about that. Yeah.
Okay, thank you.
Okay. Let's move ahead. So now we talked about this trick. Now we have reached the part where we have ROIs. Great. Uh, I probably have a lot of ROIs. This segmentation mask alone gives me like probably more than 10 ROIs, just because you can see like there are so many masks. So uh, yeah, I have a lot of ROIs. That's another problem. Then let's talk about spatialize. But before spatialize, there's a big part that we are missing, which is how do you go from ROIs to generating audio? So this is where most of the zero shot method comes into play. So uh, uh, so the existing pre-trained model that we have generates is already good at like generating mono audio from images. So in this step where you do like ROIs to generate audio, you just have an existing diffusion model that can do mono audios. So uh, so that's how the generating audio part happens. Uh, but you still need to like get some spatial audio out of it. So that is what we'll talk about next. So so for spatial audio, what we do is we end up with a simulation. And in our simulation, we have all of these sources. Here I have three sources, for instance. Uh, and these will be all the mono audios generated by the diffusion model in the previous step. Uh, now, uh, now there's also depth estimation that comes into play here. So what we'll do is we already have the x and y positions from the on the image or on the panorama or whatever we you want. you already have the X and Y positions of like each ROI just from making that contour earlier and all of that stuff. You also need some kind of depth, so you can like place it on this, as we call it, this viewing sphere. Uh, so 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 that is why you also need depth estimation to get like these 3D coordinates to place them on the viewing sphere. So now that you have 3D coordinates, X and Y from when you found ROIs, and Z just from when you did depth estimation. Now you can place them on the viewing sphere, uh, and then what we do is we use something called image source, and we slightly modify this. So the way we do this is you place all of these audios on this viewing sphere. So this is the viewing sphere actually. I just make it bigger, and then you place multiple virtual microphones in the room, and then you just do a simulation of how the spatial audio would look like. Uh, w- well, that this is not quite true. I missed some details again while talking about this. So let's talk about some of the details while we are trying to do this simulation to get spatial audio. Uh, so the first thing is audio channel isn't at the place that the object is. So, for instance, let's see this again. You have source one, which is at some position on top right. Uh, but the six audio channels I have, none of those audio channels are at source one. Uh, so um, and well, you could like theoretically have these audio channels at the exact same place that the sources were, which would be really compute intensive, and also probably your hardware by default doesn't recognize that kind of audio at all. Uh, so what you need to do is you have some source positions, and then you have some receiver positions, and then and probably and over here, because we try to like make spatial audio that can be like played on all kinds of devices, you end up with like having these six receivers which we had over here. So you have these six receivers. What you then do is compute this impulse response, and the way this happens is uh, you you essentially run a simulation of 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 what the early reflections of the audios would look like. Because you have all of these audios coming from different places, it could very well happen that two of them have interference of some sort, or there's like some sort of reflection which changes where you perceive the audio coming from. Uh, so, which is why you have this alpha M term, which is all the attenuation you get due to reflection. Uh, so what you do is by a simulation, uh, you you find all of these impulse responses. Uh, and now that you do that, you notice that you essentially by just like having this attenuation factor, you end up like factoring in all the early reflections that the audio could have, the reverberation the audio could have, and that kind of stuff. This still doesn't take into account a few popular effects. I'll talk about that in like a few limitations. But essentially, like one of the thing that might come to your mind at this stage is uh, these aren't the only things that affect how audio is perceived, especially if you're perceiving any background noise. A lot of it is also affected by the scene itself. For instance, let's say you're in a movie theater. uh, you'd often see that uh, at least like early movie theaters had this had wooden and all of these noise absorbing materials. uh, so you don't have so you don't perceive sounds coming from various directions, and there's like not a lot of reflections and echoes and that kind of stuff. So for instance, these kind of properties are not at all taken into account here, and that's true. That's I think that's there have been some works that try to do that, but it's sufficiently hard for this problem, and I think that's an interesting thing to do as well. Uh, but if you just see this, that's not being done over here. Yes. So then what you do is now that you have this impulse response, so there's this H and then you have this HCH. So so the difference between both of them is this, that you have impulse response for each channel. So you had the 6 channels over here, and we are calculating the impulse response or the perceived audio for each channel. So you end up with like these H values that you calculate through a simulation for each of the channels, and then you can convolve them with the original audio. So I just represent that as A over here. So then you can convolve this for the original audio, and then you'll get a perception of listening to the spatial sound. Great. So now,
Sorry, one question here. Sorry, in the previous slide. So, what does it's so HCAT represents the it represents like all the source or like the deflections and like I see, it reflects all like the strength of the incoming like audio signal from like each source, and then by convolving it with the original audio, you actually get the final like realistic audio. Is that the basic idea?
yeah, that's pretty much like the basic idea.
Okay.
Exactly. Yeah.
Thank you.
Okay, I'll move ahead. So then there's talk about evaluation, and evaluation is super tricky. Uh, you have all of these evaluation methods for 2 channel audios, and I know that there are some evaluation methods for spatial audios as well, and they somewhat work sufficiently different from what we want to measure. So we also do a human evaluation, but I won't show that here just because. Yeah. Let's not talk about human evaluation. The results seem to be good, but yeah, that's human evaluation. Let's talk a bit about quantitative stuff. So the thing that we okay. So the thing that we do is we propose this way called marginal scene guidance, uh, and this is partly inspired from what other areas in vision have done, especially for text to image and text to video. When we ran out of like really good ways to evaluate text to image and text to video, uh, we ended up with using other models to evaluate models. Uh, so the inspiration mainly comes from there. So what we do is we use this model called Avatar, and that allows us to measure the scene guidance. So given you have some static image, and then you have some audio, Avatar edits the audio, solves an audio editing problem uh, for matching the audio to the scene that you gave it. So that's what Avatar does, and essentially what we try to compute is see how different Avatar edited audios are from our original audios. So if you have a higher similarity between edited audios and the audios that you generate, uh, you probably end up with a method that really matches the scene guidance or really is close to what the scene represents. So that's how we also do this eval and get what we call marginal scene guidance score. So
Hey, a
that's
tiny question here. Sorry to interrupt. So, how is the similarity being calculated?
Oh, yeah. So over here, I have like all of these columns, and each of
Hmm.
them measures an audio similarity metric. Uh, so you see
Okay,
things. So you have
understood.
like dynamic time warping in the first one, which is a popular
Okay,
method, and uh, yeah. So all of these columns just represent different measures for audio similarity.
okay. So there's not one baseline metric that you're using, right? So it's a mixture of all of these metrics.
Yeah, yeah.
Okay, got it, got it. Thank you.
So that's how we do some evaluation as well, apart from human evaluation. Uh, so yeah, that's about uh, a short story of SEE-2-SOUND, and yeah, essentially there's this one link you can go to, which is the project web page, and it has links to everything. It's like the code, the Hugging Face space, the paper, the results. You can also hear some things. I guess like probably one thing to mention is that if you're trying to hear something, make sure that your hardware supports spatial audio. A lot of hardwares don't support spatial audio. Um, and in principle, if you have like a single speaker, uh, I don't know if there's like any modern ways of doing this, but in general, if you have like a single speaker, you can never get spatial audio from it. Just because yeah, you wouldn't have like stuff coming from multiple ways. So just make sure if you try to listen to any of these that your hardware supports spatial audio. uh so I guess I'll quickly touch on some applications and problems as well. So the original applications that I kind of thought of was, of course, you can pair this with generative vision models. But another interesting thing you could do is also like, uh, especially these days, you have all of these very large scale nerf representations. So people have tried to do stuff like use use large scale nerfs for showcasing an entire city or showcasing an entire patch of road or something like that, uh, which is a quite large scene and some kind of small world. People have also tried to do this with generative models, like generative video models. Uh, so I think that would also be really interesting to see pair up with this, particularly because we only focus on background noise. And yeah, I guess like another thing we thought about was also some kind of clinical applications like impurities and stroke and that kind of stuff that this could be used for. Uh, and this isn't problem free. There's all these things that I talked about, uh, and how it seems to work well, how it's zero shot, and all of that. But there's also like a few limitations at this. Uh, so the first interesting thing to try out would be like find some way of making it work end to end. Uh, so this is exactly what I started with and failed, if you remember slide two. So, uh, but I do think this would be a very interesting thing to do. Uh, if you can like find some way of doing this, yeah. And probably another thing would be on evaluation. So this definitely needs better ways of uh, evaluating the generations. Right now, the main quantitative evaluation we rely on uh, is like using the avatar model. Maybe like you can also switch it with some other model that does this task. But there's also maybe like an interesting avenue would be to like think of like good evaluation methods for this kind of stuff, for like multiple channel audios. And another problem is also about like minute visual details, so those aren't always captured. And this isn't the problem that you can solve just by zooming in or like making the image larger, right? So that's also an interesting uh, avenue. And I think like the other interesting avenue is um, I also particularly interested in like seeing if you can do this with spectral volumes. or just like some kind of uh, discrete motion maps or optical flow maps. Because so what happens is like uh, in general objects don't generate audio, right? There are very precise motion patterns, and those motion patterns generate audio. um, so it's very hard to like get all of these precise motion details just from this kind of methods. So I think it would also be really interesting to see if you can do this on like spectral volumes or optical fold maps. So yeah, that's all. Uh, and if you have any questions, feel free to share those.
Thanks for the presentation. One question I had was like this method is zero shot obviously, but like do you think it's possible to like given like a image and 3D audio dataset to somehow train a part of this to like further improve results, or like do you think more effort should be put into the let's say like improving like the diffraction stuff with like the reverberation and stuff to improve audio quality?
Yeah, yeah, we could like probably do that. Uh, and it should be, yeah, it should probably be like quite doable because most of the spatial rendering pipeline is almost fully differentiable. So we should be able to do that. But yeah, I think it would be interesting to see if there's like some nicer ways of like doing this rather than just back propagating through all the models, like the whole pipeline that I showed. Yeah, I think that's a very interesting thing to do as well.
Oh, is it even possible to like propagate through all of them? Like it feels like some parts are like not like gradient possible kind of thing.
You could probably do it after the ROI generation. So once you generate ROIs, after that you could probably backpropagate through the whole thing. And you might need some like changes in how the simulation happens. But yeah, I think like it would be nice to try this out. I haven't tried it out, but uh, yeah, I think like uh, I think what you mentioned is true. Like in the current form, it shouldn't be possible to like backpropagate through the whole thing. But if you can just like find some way to like do some stuff, change some stuff in the simulation part, then you can probably like do a backpropagation after the ROI generation, right?
Yeah, makes sense. And one final question. So for finding the 3D coordinates, I think you use the depth estimation model and stuff. But like, I don't know, kind of like out of the components, which component do you think needs the most improvement for further improved results, in your opinion? Like the segment everything ROI, or like the audio generation or the depth estimation for 3D coordinates?
Hmm. I Yeah, that's a good thing as well. I I think like probably the most improvement is needed in how you generate the ROIs. And because like the most, at least like in my i- in my mind, the most obvious improvement to this is that you want to generate the ROIs some way that they have motion information encoded somehow in them. Uh, so so probably like the way you go from segmentation to I think that's the part that could use the most improvement. Uh, and particularly, I think like encoding motion somehow into doing that would be really interesting to do.
Makes perfect sense. Thanks.
Hi, thank you so much for this presentation. It's been pretty insightful. My question is actually pretty similar to Chad's. I was going to ask if there were any limitations that you may have noticed with the um, with the depth estimation and the segmentation, and how they may have affected like the spatial audio generated. Was there anything there that you noticed?
Yeah, so there's also the other thing about uh, so one of the things that I was talking about was uh, these minute visual details, which in real life can often be like the most important parts of what you hear, uh, even if they are like minute parts in the scene. And I think like this part uh, is particularly harder to do with like all of these segmentation and depth estimation models. I think like depth estimation models are somewhat great at it, but it's hard to do these. And another thing is also that you have like all of these depth estimation models, and they uh, or like even segmentation models, and they don't really understand occlusions. And even like so for segmentation we just use segment anything. SAM2 wasn't out yet, but uh, and we also like just wanted to use an official segmentation model, but like a big problem of it is like also occlusions, and any occluded object becomes really hard uh, for the rest of the audio generation process. So I'd say these are the two problems, at least in my mind, that I came across, uh, like minor visual details and occlusions.
Nice. Yeah, thanks. Just one final question. Something else that was very interesting that I think you mentioned was how like the scene itself, right? Like the scene itself could involve maybe you know like maybe it's able to absorb sound, right? Or maybe it's a scene that reflects sound a lot. Do you have any thoughts yet on how maybe you could like incorporate that maybe in like future work?
Mm. Yeah, I think that's a good question as well, and that's also a hard problem to do. Um, it were a different thing if you said if you just pass it through the text prompt. So I missed one thing, which is you can also give text prompts, but so it's a different thing if you can like just do it through text prompts, and through text prompts you can probably like train models that you can like do for fixed audio effects, and you say, okay, uh, say that there was wood all around the scene, and there's like no sound being reflected at all, everything is absorbed, and that would be a different thing. You could probably train a model to do that, uh, but I guess it's a different problem to like understand these from the scene directly instead of doing these through the text. uh, so I think understanding these from the scene directly is a hard problem. uh, One way to probably do that would be if you can just like do the end-to-end thing, right? Because then you have embeddings for the visual media, and then you can, if you have like enough stuff in your training data, then you can assume that the embeddings also take into account the textures and materials that are in the scene. Uh, so I think that those are the two ways I think of.
Yeah, awesome. Thank you so much. And I do agree with you. If there was a way to train a model to understand the scene and understand the composition of the scene, that would be the best way to train it end to end. Yeah, thank you so much again for the presentation and for uh, you know, thank you.
I have a question for you. Imagine we have a slow-mo cameras picturing every frame second, 1,000 frame each second. Can we give this model and slow motion sound effects? can we are fine-tuning the model? Is it possible?
Oh, so did you say, is it possible to fine-tune the model with some kind of motion cues? Did I get that
Uh,
right?
no, no. Slowing the sound effect in real time, causing the faster can be rewind like a video or slowing the sound effect.
Oh, yeah, yeah, all of these sound effect things are also interesting to do. Uh, I think like so I haven't tried that out right now, but I think like an interesting way to do that would be to do the text from thing that I was talking about. Uh, like probably make an instruct pix to pix style data set and fine tune just the audio generation part of this pipeline uh, with text prompts to do all of these things like slow down audio or incorporate textures and any of these things. So I think that would be one of the ways to do it that comes to my mind. But yeah, I haven't tried that out. Seems like a interesting thing to do.
Are you sorry, am I off video? Sorry, am I off audio? Can you hear
No,
me?
I hear you. I hear
Okay,
you.
great. Have you introduced this to any of the movie studios in LA?
No, I haven't.
That might be something to put on the follow-on list. I mean, they all have, divisions that are technical people working on related things, or they've started it. So, might be interesting to run by them.
Yeah, sure. That sounds interesting. I can like probably try to see how to reach any of them out. But yeah, thanks for the suggestion. Yeah,
Yeah,
suppose.
I would suggest getting in terms of how to do that. If I were in your shoes, I would get LinkedIn Navigator if you don't have that yet, and then use LinkedIn Navigator to look to kind of piece together an org chart to get connected to the right people.
Okay. Thanks for the suggestion. Yeah.
Thanks for the presentation.
There might be some questions in the chat too, I
Oh,
think.
yeah. I can take a look at this. Yeah. So one of the questions is about evaluation and there being multiple ground truths. So yeah. That's always a problem. You have all of these problems like image denoising, for example, or image generation, or many times language to language as well. And many of them have like multiple ground truths. So yeah. I guess like that's a problem in general. Uh, Throughout like multiple fields about how to best evaluate those kind of models and any of these ways of doing like using another model to evaluate a model, those come very close because they because then you're like doing the similarity and that kind of stuff on the embedding space. So that's probably slightly more indicative of if it works well. But I do agree that that still is like a problem with evaluation. I think that's the only question I see. Another seem to have been answered.
There's like one question about how do you eliminate unnecessary or irrelevant segmentation? Did you have an issue with that?
Oh, yeah. Yeah, I can. I don't know why I don't see it, but yeah, I might just be like at the wrong place in the chart. It's very long. But yeah, essentially, that is a problem. Like, you often end up with like a lot of masks because um, any of the scenes that you have will often have a lot of individual objects. So that is true. Um, and the way to do that is like right now we just uh, use some heuristics to do that, and uh, try to bound like uh, how the how try to bound like how the ROIs are generated, and how you can, and how many and which of the ROIs you'll use for the diffusion model. So for a lot of what, like it just works because when you because even if you do like all the ROIs in the simulation, you'll end up with pretty good sounding audios, because there would always be like some interference and that kind of stuff. So they would be drawn out by like the major objects in the scene. Uh, so you can still do that, but like a better way to do it is, off the top of my head, probably just use some heuristics. You can modify the method to do that. Uh, right now, it just works if you use all of them as well for simple scenes.
Got it. Thanks a lot. Interesting. So there is like a set number of bounding boxes that you have. So I guess it also helps in computation too. Maybe. Yeah.
Oh, so a slight. Oh, so I was saying like you can also use these heuristics to compute like a fixed number of bounding boxes. Uh, so that's like a thing off the top of my head that could like that you could do. Like all our evaluation and in the paper we don't do that, but because the simulation part handles it itself. Uh, and you have like all of these smaller details with very low audio, so you don't have to worry about them so much. If you see the Hugging Face space, the number of different bounding boxes you have directly impacts how much GPU you need, or how much GPU time you need. So in the Hugging Face space, it's limited to uh, I believe I limited it to like three or four in the Hugging Face space, just to like make it be done in like 200 seconds approximately. Uh, but yeah, if you like see our experiments in the paper, those don't do that.
Got it. Thanks a bunch. Yeah. Does anyone have any other questions?
I have one last question. Thanks for representation. For cybersecurity area, I'm think of uh, some people can expose the machines to fast speeds or CPU sounds like. Can happen this issue cause problems in cybersecurity area?
Mm. I think like uh, if I got the question right, like the problem is like about deep fakes and that kind of stuff, right?
Yes.
Um, I guess like at this stage, so this is less of a this is less of a problem because we aren't doing speech. So you can't. We are only doing background noise. So I guess that's one thing. So it's not as much of a problem uh, as like doing speech. But the other thing is like yeah, probably it's of course a problem with all of these generative models, and I haven't explored a lot into that. Uh, but yeah, probably it would be good to like have some kind of guardrails on this kind of stuff, like methods to ensure that this doesn't happen. But yeah, at the moment, like I haven't explored that area at all. I think it's a very interesting research area to like do all these trustworthy models. Uh, but yeah, I just haven't worked in that area at all.
Thank you.
One last question here. So, this might be a dumb question, but does this pipeline assume the position of the receiver, or can it be dynamic?
Uh, so the pipeline. Okay, so I think I'll break this into two things: the pipeline and the code base that we have. So the code base that we have that assumes positions of the receiver. It's actually static. Uh, you can like probably find a line in the code where we explicitly mention what position the receivers are at. And the reason we do that is because so there are a few standards around how to generate how to play spatial audio. So if you have a speaker at your home, a home theater, whatever, it probably uses those standards for how to represent spatial audio, uh, how to make that and that kind of stuff. So if you want to follow those standards and play them accurately on these devices, then you need the receivers to be at the proper locations. But but yeah, you can of course like increase the number of channels or like have dynamic channels wherever you want them and play them somehow. Uh, yeah, you can like most certainly do that. So the pipeline does not make any assumptions, but if you try to like as it is on any of our code, you'll see that there are static positions just because we want the hardware to be able to run it.
All right, understood. Got it. Thanks.
So I guess like that's all the questions. Yeah, thanks for hosting this.
Thanks for presenting, and yeah, hope everyone has a great day. The next presentation may be about like hacking with LLMs, yeah, not decided yet. But yeah, again, thanks Rishit for presenting, and hope you get a lot of citations.
Thank you. See you folks later. Bye.